Okay, so I thought the question the other day came up, or I mentioned what happens as you increase the link to the threshold voltage. I got a question about why this happens. Why does the threshold voltage increase? And then I decided, well, let's go plot this, because fundamentally it's a second order reason that threshold voltage decreases as a function of increasing length. And it used to be that in short channel bulk CMOS, in order to get the devices to work the way they want them to, they dope all around the device, and all those dopants cause all kinds of stresses on the device, and the effect of those stresses reduces as you increase the length of the device, and that was what was causing it. Now, in the fully depleted SOI process that we're using, fully depleted means that they haven't doped at all under the channel, so they are not putting they're not doing stress engineering under the channel. So I went and swept length and measured threshold voltage, and lo and behold, I'm wrong. Well, at least in our process, if you increase the length, the threshold voltage will increase. Yeah.
Couldn't they still stress the channel by changing the drains? They
do. You don't have, so they have non-native devices, but for the native devices, just the normal InFET, normal PFET, they have not put any dopants under the device. They're only doping in the drain and the source region. They dope under the channel to engineer the threshold voltage. Essentially, they do that in short channel devices because they need to engineer when they turn the device on and turn it off, because they've just effectively lost control of the channel, and so they're trying to regain a little bit of that with dopants. Now, then. Is a terrible position for the mute button to be. So then I said, okay, well, we do have we actually do have a few bulk processes, but I'm not using them right now. So I wanted to see, okay, what happens with a fin. So this is sweeping the length and measuring threshold voltage for a fin, and I'm trying to confirm if this is real or not. But it does kind of do what I would have expected a bulk transistor to do in the past. As you increase the length, the threshold voltage would start to roll off. I'm trying to decide if this is an anomaly. But with fins, part of the problem is that there are only certain geometries that you can use with the fin. You can't just continually scale the length and width of the devices. They have kind of fixed pitches that you can use. And so this could just be an artifact of the model at some weird, weird combination of width and well, it's not even width. It's number of fins times number of gates. So fins are kind of discrete devices, but anyhow, this is kind of what I would expect from an old bulk process. Yeah.
Is that something continuously from like 20 nano to 80 nano, or is it just regular volumes?
No, because when you try and use the device, the fin device, so there, if I try and just put some random gate length in, took 20. See, I tried to put 30 in, and it forces it to 28, and I think the next step was like 80. Yeah, so anyhow. It turns out that the way that we change the length in a fin device, we tend to stack devices. It's easier to stack them, so that's much more common with fins. Okay, any questions on that? So it's really a second order effect, or maybe a third order effect, that's causing the threshold voltage to vary as a function of length. It doesn't show up in any directly in any of the functions for threshold voltage, but just more due to the way that we have to engineer a modern device to get it to work. All right, now we were playing. So you have an LNA assignment that's finally due this evening. So I wanted to spend a brief couple of moments talking about LNAs. Let's close some windows here. I think Peter approves.
Yeah, maybe all the other users on the cluster approve too.
Most of these are sitting idle. They're not really using memory. Okay, so one of the things that we showed in simulation is that there's an optimal current density for a device in order to operate and yield the minimum noise figure. And that's pretty consistent whether you're using bipolar devices or MOS devices. For a given width, you need to have a certain current flowing through the device, and that's going to give you the possibility of achieving minimum noise figure. Now, that doesn't necessarily mean it's going to be easy to achieve minimum noise figure. It just means that, at that current density, you're going to achieve it. The paper that I uploaded from Sean Nicholson and Professor Soren Bonescu just before class kind of goes over maybe a more optimal strategy for minimizing noise figure. And in this, you'll notice he does say step 1 is to optimize the biasing, so figure out what the current density is and use that. And then in step 2, he says size the device until the real part of the optimal termination impedance to get the lowest noise figure is equal to whatever impedance you want to match to. So, for instance, if you want to match to 50 ohms, keep increasing the device size until you hit 50, until that circle intersects with 50 ohms. That's great. The problem is with low frequency LNAs, it tends to make pretty big devices. And since the devices need to work with a certain current density to yield their minimum noise figure, it might mean using a lot of current also. So his methodology doesn't optimize for power. There's an older methodology by Derek Schaefer, who was Tom Lee's PhD student at Stanford, that optimizes, that kind of puts a bound on power as well, if you want to look at it. But let's look at what the implications of this are. So here, instead of sweeping current density, I fixed the current density at 700. When I swept this earlier, hopefully you'll recall, I found that the optimal current density was somewhere around 700 milliamps per micrometer of gate width. So here I'm going to just put that number in, and then I'm going to sweep the width of the device, width of a finger, and I have 32 fingers and 8 parallel devices. So if we want to look at where all that is in the device model, here I have a multiplier of 8. That means 8 parallel devices. 32 fingers is the number of individual fingers in one of those 8 parallel devices, and then I got a variable set for the finger width. All right, and let's go ahead. So I'll run a simulation here. All right, I'm going to come back to this in just a minute, but I can go in and plot this G-min. G-min is the optimum noise reflection coefficient. So this basically tells us what reflection coefficient we need to present to the input in order to achieve a noise match. And you can see for this relatively big device now, as I sweep the width of a finger, I do have something that starts to intersect that 50 ohm line on the Smith chart. So this circle right here, the unit circle, is 1 normalized to 50 ohms, or normalized to a characteristic impedance of 50, that's 50 ohms. So that's good. It takes a very big device to do that. You can see the device width is 3.05 microns. That's the finger width times 32 times 8. So this is a big device. In fact, if we wanted to achieve optimal current density, it would be about 500 milliamps of current. I think I told you to use 1 milliwatt, so not going to happen with a device like that. So that's kind of the trade-off. At low frequency, you need really big devices. Now you can also go in and write some equations. So here I've written an equation to get whatever the characteristic impedance of the simulation was, and then I take I find the real part of that G-min, the imaginary part of the G-min, and then I write an equation to find the real part. So this is basically 1 plus gamma over 1 minus gamma times Z naught, and then I take the real part of that, and that gives me the real part of the impedance. So if we plot this, now you can see, that it crosses 50 ohms somewhere right around 3.05, hopefully, because that's, what the Smith chart is telling us. Okay. Now, what do you do if you have a power constraint? You kind of do the best you can. So you need to go back and constrain your power and kind of figure out like what's the closest I can get to 2 dBs. It's not an easy design. Okay, and then last but not least, we have been talking about Class E amplifiers for the past few days. So I thought to kind of build an ideal Class E amplifier. So I added a library into Cadence. If you aren't seeing it, you can go into your library manager and hit View Refresh, and it will hopefully add this Walling AHDL library in. These are AHDL is or they call it Verilog A. It's just a hardware description language that allows for analog voltages and currents to be used instead of just assuming digital stuff. So here's a non-ideal switch. I call it non-ideal NMOS switch. And if we open up the tools filter here to Verilog A, you can see I've set the threshold voltage at 0.4 volts. I made the switching resistance a variable, and I just left the off-state resistance to be a very big number, 100 mega ohms. It's probably big enough. We don't need to mess with it. I have RL here. This was the load impedance that we would calculate, given based upon the notes. And then I have the series inductance. This is X opt, B opt. I'm using a choke in this particular simulation, or at least something that's pretty close to a choke, 100 nanohenries. And then I calculate whatever these components need to be in order to achieve resonance. And these are all just, they're entered as variables. I wanted basically everything in terms of FRF, RL, and the supply voltage, if possible, and Q, the network quality factor. Okay, so the only thing that we calculate in this variable list, well, I guess we calculate two things, but one is RL. RL is 0.577 times VDD squared divided by P out. Now, one thing you'll notice about Cadence, it does not have a caret symbol to square something. You use the star star And then minus 2/3 R switch. I have R switch as a variable. I'm making it kind of small, and I'm just determining I want to get a 1/4 watt P out. And I know this isn't right, and I know why, because I forgot to divide by, I forgot there's a 2, factor of 2 here. Okay, now in order to find the so there are, oh yeah, a few more things. I set a stop time here. I make it a variable, and I make it 500 periods. Now, you don't always need to make this 500 periods, but this is a fairly ideal circuit. There's not a lot of resistance in here, and there are a lot of reactive components. When you're simulating with a lot of reactive components and not a lot of resistance, it often takes the circuit a long time to settle. So here I'm simulating for 500 periods. Of course, I could change 500 to something shorter if it settles faster. We'll take a look at the plot in just a moment to see. I can then use that variable in my transient simulation just by using this function var t stop. By the way, this is in my ECE 5984 RFIC library called ideal _ class _ E, so you can open this up and take a look at it. Okay, and then if you want to evaluate well, let's first of all look at the waveforms. Let's see if these look like class E waveforms. I ran this a little while ago. All right, so one thing you can immediately see is I've run this for 500 periods and it hasn't quite settled yet. If I look at this, it's still, you know, the amplitude of the wave is still changing out here. So need to go even longer. But I think we'll be able to look at the waveform and say, like, does this look like a class E waveform? I think this kind of looks like what I showed you, the voltage waveform here. The green waveform kind of, you know, goes up, goes down, and then tries to kind of level out before it gets back to, before the switch turns on. The purple waveform is the switch turning on. So it's not perfect, but close to perfect. Let's see, the current waveform is, okay. So the kind of idealized version of this thing, the current waveform just kind of ramps up linearly, but in reality, it'll start to kind of discharge through the capacitor a little bit. So this is a class E waveform. If you go to the paper, you'll see a waveform that looks like that. And the output waveform here looks like a sinusoid. It's kind of distorted, but it looks like a sinusoid. So pretty good. You can see the voltage waveform, the current waveform. They don't overlap very much, so it should be pretty efficient. It does look like a class E. Now, I go through and write some equations in order to figure out what the output power is. Let's run this again for a longer period of time. And while I'm at it, also teach some good habits. All right, we're going to run a long transient waveform. That means that we're going to have a lot of data in order to not kill the server. It's good to go in the transient simulation. If you go to options, output, you can go to save selected, and it'll only save the selected nodes that you're looking at. So that's a good idea. All right, so we'll run this for some period of time, and I'll explain to you what all this stuff is doing.
Would this be a good time to use there's like what's called like POP, periodic operating something, like they'll have some analysis that does this for you, or just like waits until it's steady state? So
there's one called PSS, periodic steady state, and that PSS would work, but sometimes it takes a long. I mean, fundamentally PSS is going to look for convergence, which means it's going to look for two periods back to back that are within the convergence limits.
Yeah.
So it's going to do the same. It's going to have to run for at least as long as the transient simulation has to run.
Yeah.
Now, maybe not quite as long as I'm running here. Let's see what the waveforms end up looking like if we. Yeah, I'd say it's close enough to being settled out there. I mean, the only way to really tell would be to actually go to 2 consecutive periods and see, are the voltages and currents at every node in the circuit identical 1 period apart from one another. That's what a PSS is doing. This looks pretty good. So it's yeah, looks pretty nice. Okay, so what I'm doing here is basically a little cheap version of a PSS simulation. So I set an end time, which I just said is basically whatever the stop time I set over here is, and then a start time for my analysis, and I just set that as the end time minus 2 periods of the RF waveform. So we're just going to look at 2 periods of the waveform. Because we don't know if it's converged within the limits, looking at 2 periods is going to basically average any effect. We can find the DC current by plotting. So this function I use clip, which takes just a section of the waveform from T start to T end, and I take the average of that waveform. That's the same as finding the DC current. And then to find the drain power, I multiply that DC current by the supply voltage, VDD, and find that it's 272. My RMS output voltage is found by taking a DFT of the output waveform from T start to T end. So we want to make sure we get exactly an integer number of periods here, so that we don't end up with folding information into the wrong bins of the FFT. So that's what the function is designed to do. It applies a rectangular window in case we do accidentally do that. That'll help the analysis, and then it finds the value at a frequency. It linearly interpolates the value at a frequency of FRF. So this DFT is going to put out a spectrum, and I just want what's the fundamental component. This whole thing gives me the. It doesn't give me the. It gives me the amplitude of the waveform. Of the fundamental component. I call it RMS here. That's not right. It should be called amplitude. Fix that. And then to find the output power, we divide by we square that and divide by square root of 2. Sorry, we divide by the square root of 2, square that, and then divide by the load resistance. That's where all of this stuff is coming from. And the net result is I told it to design it for an output power of about 1/4 of a watt. It's at 266, so it's pretty close. There are some non-idealities that we're not accounting for, like the kind of overshoot non-idealities and things like that, which will account for the differences. But anyhow, pretty quick and easy way to design a Class E amplifier. And then all these things are really kind of doing exactly what the PSS simulation does underneath. They're just using the calculator function instead of letting PSS do it for us. Yeah.
We're basically looking at only talked about at the fundamental. We just ignore every like harmonic.
Well, so if I was doing, if I was going to further look at this, I would also find what the distortion is and look at the harmonic components as well. Yeah. You can see there's a minor discrepancy between P drain and P out. That means power is going other places that we don't want it to go. Some of that could just be thermal dissipation, but some of it could be it's leaking into harmonics that and contributing to the harmonic content. Of course, I also set a relatively low quality factor here, so that plays a role in this. If you set the quality factor higher, it's going to take longer to settle also. So. Any questions about that? All kinds of, Cadence is a really powerful tool, all kinds of things you can do with the calculators and simulations. So if you have any questions on any of this, just let me know. Okay. Let's go back to class F. Okay, so the class E waveform, I think somebody asked me the other day, like, how do they dictate, or what came first, maybe the waveform or the and I'm not sure what came, or the waveform or the network. I'm not sure. A lot of people that came up with these things initially, they were just kind of tinkerers. They would kind of play around with stuff and get it to work, and then they go and figure out why it worked. So I don't know. The class F was presented by there's a guy named Matthews in the Marconi review. I need to dig that paper up. It's actually a hard paper to find. But the concept is still the same. I want to create non-overlapping voltage and current waveforms at the drain of the transistor, because if I do that, that means the transistor dissipates no power. And so, hypothetically, here's a way that I can do that. So for instance, I have if I square my voltage waveform, and just because of the way I'm going to do the analysis later, it'll be easier if I draw this way. So if I half rectify my current waveform and square my voltage waveform and get them to non-overlap with one another, then I'll also dissipate no power in the circuit. So, looking at the class E, this is a power transistor. It's got some drain current flowing through it, and it's got a drain voltage. And the average value of the drain voltage, what's the average value of that drain voltage? It's VDD. It's going through an inductor, and it'll be VDD. So, but we've shortened it to where it's only there for half the period, so it's going to have twice the amplitude, whatever. Okay, so how do we create these waveforms? Well, if I look at the drain waveform and I do some Fourier analysis, I can find that the drain waveform looks something like VDD plus the sum from n equals 1. So all of the odd harmonics up to infinity of 1 over n times the sine of n times theta. And for that half rectified current waveform, we can again do a similar analysis, and we're going to find that it's equal to IDC plus the sum from n equals 2, 4, 6, all the even harmonics up to infinity of 1 over n times the cosine of n times theta. All right, so this is telling me something about how I'm going to get these two waveforms. Somehow I need to make all of the odd harmonics appear in the voltage waveform, and I need to make all of the even harmonics appear in the current waveform. I've got to come up with some network that's going to do that. Before we do that, let's look at the what happens if we are able to make these waveforms. So we can find the DC current if we integrate from 0 to pi over that waveform. Well, I should say the waveform only exists from 0 to pi, so we're going to integrate from 0 to 2 pi. All right, so we can find the DC current. It's going to be something like IS over pi when we integrate across the full cycle. The fundamental current, so we're just doing Fourier analysis, 1 over pi, integral from 0 to pi, IS times sine of theta, sine of theta d theta. This ends up being IS over 2. The DC voltage, same thing, integral, 1 over 2 pi, integral from pi to 2 pi, since the waveform doesn't exist from 0 to pi, of 2 times VDD times d theta. This is equal to VDD, as we would expect. The fundamental voltage component, 1 over pi, integral from pi to 2 pi, 2 VDD sine of theta plus our phase shift of pi d theta, and this ends up being 4 times VDD over pi. Now, if we want to find the efficiency, we need to find the power, the fundamental. So this is going to be the fundamental current times the fundamental voltage, and these these need to be converted to RMS. So we're going to have a half. All right, so if we've done everything correctly, the numerator completely cancels with the denominator, and we get an efficiency of 100%. So that's what we're going for. Yeah.
The voltage waveform Fourier series makes sense. That's just the sync amplitude, sync square. The current waveform, how did you get that? Is that the Fourier series from half?
It's a Fourier series for a half rectified sine wave. Yeah.
I tried recreating it. It's pretty. Looks like that. Square wave looks fine.
Make sure that you have the right offset on the waveform.
Regardless of the offset, it should still show us the same shape, right?
It should. I have to think about that. I'm pretty sure the math is correct, but I'll. Okay, so how do we create the situation that creates these two waveforms? Fundamentally, I want to have a high voltage at all of the odd harmonics. So what do I want my impedance to be at the odd harmonics? If I want to realize a high voltage, I want it to be a short circuit, or do I want it to be an open circuit? Open circuit, right? Yeah, so I'm just going to say a high impedance at all odd harmonics. And this, this will yield a square-like voltage waveform. Okay. Now, conversely, if we want to add all of our currents, we want to have high current flowing through the device at the even harmonics. That means we want to short circuit the output. So I'll just say a low impedance at all even harmonics. Okay, now we can calculate, what the essentially what the impedance is at the fundamental frequency. We just calculated what the value of the voltage and current were at the fundamental, so we can find the impedance. That's just V fundamental over I fundamental. So we have 4 times VDD over pi times 2 over IS, or 8 over pi times VDD over IS. Of course, we did already calculate our output power, but I didn't write it out expressly. 1/2 times 4 VDD over pi times IS over 2. And from this, we can solve for IS in terms of the output power. And then we can plug this back in and find what R opt is as a function of output power. All right, so that's pretty good. Is that better or worse than a Class E amplifier?
Series ones.
Better than the series, worse than the parallel circuit, right? So we have a factor that's greater than 0.577, less than 1.365. So pretty good. Better than any linear amplifier. So if we want to, make a Class E amplifier, really what we need to do is at the fundamental frequency, we need to present this R opt, 8 over pi squared times VDD squared over P out. At all odd harmonics, we want the impedance to go to infinity, or as close as we can get it. At all even harmonics, we want the impedance to go to 0, or as close as we can get it. All right, so let's look at some ways that we can do this. Well, the first way that we're going to do this is we're going to try and use a transmission line. All right, I'm going to put a DC block in. So this is a DC block. This means it's a big cap. BFC, as Tom Lee would say. I've got some transmission line. This transmission line, has a value of Z naught at, and it's a quarter of a wavelength long, so lambda by 4. I'm going to add a resonant network. And I'm going to put a 50 ohm load at the output. Now I want to be clear right now that I'm not necessarily saying that Z naught is equal to 50 ohm. Z naught is something, it's just the characteristic impedance of the line right now. So this network is resonant at our switching frequency. So our switching frequency is the frequency of this waveform that we're switching the input. All right, so what is the impedance of this of the tank at the fundamental? What does the LC circuit present? It's infinite. Yeah, that's right. So it's an open circuit, so it's not loading.
That was infinity.
I got you. You weren't doing the what is it, the heart sign? Yeah, so the impedance is an open circuit. It doesn't load the circuit at all at the fundamental frequency. So what is the impedance looking in this direction? Zn.
Wait, hang on, no.
No, because we got a 50 ohm load there still.
Yeah.
So if you remember from your microwave engineering class, you might remember that a quarter wave transmission line has a special property that's doing impedance inversion. That's what Rohit was mentioning here, but we can write this generally. It's Z naught times, I'm going to call this R antenna. Z naught times R antenna plus J times Z naught times the tangent of the electric length all over Z naught plus J times R antenna times tangent of the electric length. Of course, we've already dictated that beta times L is equal to lambda over 4 or 90 degrees. Yeah, Sean.
Would it be R out times Z naught times?
Yeah, it's sorry. There we go.
Oh, okay.
Yeah. Okay. Tangent of 90 degrees blows up, so we get infinity over infinity. We take L'Hopital's rule, and ultimately you can show that this is equal to T0 squared over our antenna. Now I want this to be equal to R opt. This is the impedance that we present at the fundamental frequency. So I want it to be equal to R opt. So I set this equal to R opt. And this tells me, okay, make the transmission line's characteristic impedance equal to the square root of R antenna times R opt. If I do that, then my network will present R opt to the transistor. Okay, what happens at high frequencies? So we have a capacitive short. So the capacitor is a short at all high frequencies.
The line like goes and changes and sweeps across. Like,
Yeah.
like electrical links.
Yeah, the electrical link will effectively be changing. So C naught is a low impedance. At all high freq. So it's like a short circuit. So at the next odd harmonic, it's going to get inverted and become a high impedance. It's good. So at every odd harmonic, we have a high impedance because of the property of inversion of a quarter wavelength line or an integer multiple of a quarter wavelength line. At all even harmonics, we've gone completely around the Smith chart back to the same point. So it's like looking at a short circuit at all integer multiples of an even of the fundamental. So this network does exactly what we want it to do. It presents high impedances at odd harmonics, low impedances at even harmonics, and at the fundamental frequency, it gives us, if we choose the correct characteristic impedance for the transmission line, we're done. What is wrong with this thing?
Between impedance and response.
We'll live with a certain amount of spurious performance for any kind of switching amplifier. Yeah, this is an RFIC class, right? So what's the, let's say we want to make this thing at 1 gigahertz. What's the wavelength? 30 centimeters. Yeah. So I need seven centimeters of transmission line. It's not good for an RFIC. Most RFIC, I should bring in some samples, but most RFICs are a couple of millimeters on the side. Doesn't work. Even if I go to 10 gigahertz, not really helping a whole lot. Still, yeah, doesn't really help until maybe we get to the millimeter wave regime, but then I can't switch the transistor any longer. So, so that's not going to work. All right, well, maybe if we reorient the transmission line. So let's try something like this. All right, so I just put my transmission line, make it Z0, lambda over 4. And I tie it right to the drain. And then I have a matching network. I designed the matching network so that it presents R opt during an impedance transformation. And now, what's the impedance at the drain at the fundamental frequency?
Just the amount of the transistor, because that would be an open circuit.
Yeah, it's R opt in parallel with an open circuit, so which is R opt, right? So it's good. So at the fundamental, this works. Now, when we're away from the fundamental, the matching network is probably presenting some higher impedance, so that's fine. So at every odd harmonic, this is inverting the short circuit from the supply voltage to a high impedance. At even harmonics, it passes the short. We go all the way around the Smith chart back to the same point. So, so that's good. Is this any better?
You have some, still you have a problem with the lambda over 4, because if you want to do it, you need to do the wire one, because you cannot do it on shape.
Yeah, so this is maybe a little bit better in that it's in the supply network. So if I wanted to, I could have the RFIC, I could wire bond the drain of the transistor directly off chip, and then I could, put a quarter wavelength line on a PCB or something like that. So it's a little bit better, but functionally it's still the same problem. This is going to be a long transmission line.
Is there a way we can make the wire bond itself cut?
We could probably make an artificial transmission line with a couple of wire bonds. So if we have the we have the center bond and then the 2 down bonds, that can make kind of an artificial transmission line. But then you're really kind of playing around with how precisely they can control just the geometry of the bond wires, right? They need the bond wires to be exactly aligned with one another because you're trying to keep the electric field and magnetic field exactly proportional to one another and propagating along the line without a mode transition or something weird like that. At low frequencies, it'll be okay, but at high frequencies, it will get kind of squirrely. Okay, so really, this is maybe a little bit better. We get the bond wire, we get the transmission line out of the series path, but it's still have a big transmission line. All right, so our next solution is, let's see if we can do something with, right.
If we're talking about offboarding like off-chip components to do it, this regardless, why not go the entire matching network off-chip in this color?
We might do that, but there are reasons. So normally the OEMs, when you sell them an RFIC, they don't want a ton. They don't want like BOM additions to their to whatever their product is. So you're already going to be having them add some decoupling capacitors and things like that. Now you're going to tell them here, you also need to add a few extra additional components plus a transmission line. Probably not going to work. You might not sell a lot of parts.
But is there some like technical restriction? Because like the wire bond, like directly to the drain, is that like that or something? It seems like it would be really, for research at least, it would be really overpowered to just like have some really high Q inductors and capacitors off chip all the time.
Yeah, people do this in research frequently, but for a pure RFIC.
Yeah.
Now, we're also talking about CMOS power amplifiers, and there are only a few niche cases where you can use a CMOS power amplifier. So. You can get away with it in connectivity applications like Wi-Fi and Bluetooth for lower power things, but for anything higher power, it's almost always going to be a 3.5, okay, a mimic. Band gap. All right, so let's think of an alternative. Okay, what if we did something like this? All right, so you put a bunch of parallel resonant networks that are all designed to be parallel resonant at a different harmonic. So for L3C3, that's parallel resonant at the third harmonic. It means it's a high impedance at the third harmonic. And then L5C5 is a high impedance at the fifth harmonic, and so on and so forth. And then I have, essentially a short circuit through either the inductor or the capacitor, depending L1 or C1, depending upon what harmonic I'm operating at. So here I've managed to do the same thing. I have a network that will synthesize high impedances and low impedances. Okay, so just using parallel resonances now. Is this good? What's wrong with this? Yeah, a lot of inductors there, so it's the same problem ultimately. A transmission line I don't want to use because it's big. If I have to use infinitely many inductors, that's also pretty big. Okay, so we do have an issue, but what's kind of nice is there was an analysis that you're going to see this guy's name come up over and over again. What if we don't terminate all the harmonics? What if we just terminate a couple of them? So there was another analysis, another paper I'll share on Canvas This was from June of 2001 in TMTT. And what he showed is that the efficiency of a class F amplifier can be found to be the product of these two terms, gamma times V, or gamma sub V times gamma sub I over 2. And these terms gamma V and gamma I depend on the number of harmonics terminated. So you can show that if you only terminate the fundamental, so that's the first case, number of odd harmonics, if you only terminate one odd harmonic, one even harmonic, then you're going to get a factor of 1 for gamma V and gamma I. That looks like a class A amplifier. Again, 1 times 1 over 2, 50%. Not so good, but he goes through it in the analysis and shows that for the first and third, gamma V becomes 1.1547, and if you do 2 and 4, gamma I becomes 1.4142. If you do 1, 3, 5, it's 1.2071. If you do 2, 4, 6, it's gamma I is 1.5. As you imagine, as you keep increasing the number of harmonics that you terminate, this keeps going up until the product of these would be equal to 2, and then you'd have 100% efficiency. So, what we can see here is, if you're looking at this table, like what would you choose to do if you could only terminate? If you could only make one choice, what's your optimal choice? Well, let's say I can only choose even harmonics or odd harmonics. Just literally one set of terminations. Yeah, you choose even. That gets you a bigger bang for your buck, right? Mm-hmm. 1.2071, yeah. And I'll upload the paper so that my sloppy handwriting does not limit our understanding of Frederick Rob's beautiful work. They called him Fritz Rob. Met him a couple times. He's a pretty nice guy. All right, so we can look to see what happens if we terminate even harmonics or odd harmonics or a combination thereof. So we fill in our table here. One harmonic, it's 50. Just the third harmonic, 58. Third and fifth, 60. And then we'll just keep filling in here. It gets better as we terminate more harmonics. All right, you can see that basically once you get above 2 harmonics terminated, things start to get better than a class B amplifier. Now, the class F amplifier is still not linear, so that is a problem. It's interesting. So if I think about this, if I go back to that prior network, maybe that is a good trade-off. I only have to make a couple of parallel resonant networks. It's something we probably can do on chip. What's interesting is over the past couple of years, if we look in the literature, there are a lot of people that have made what we call linear class F amplifiers. And the reason, the reasoning is basically if you kind of drive a class B amplifier that's terminated with a network that looks something like this into saturation, it becomes this kind of class F-like behavior. I would argue that it's just that a class F amplifier is not a linear amplifier. If you go back to the original Matthews paper, they do indicate that you can soft switch the devices, so I don't have to really like, hard switch them between 0 and VDD, and you still get good performance. But I still argue that it prefers a nonlinear waveform for operation, not a nice linear sine wave that's driving it. Okay, so we are running out of time, and so I don't want to start the next one. But what we're going to do next is just start to look at much like the class E networks. This guy Grubenikov did some nice analysis, and he showed that there were a couple of simple circuits that we can do that exhibit class F-like waveforms, namely a parallel circuit and a series circuit for the class F. So we're going to see that on next Monday. Just to keep track of where we're going for the class, I'm going to move away from power amplifiers and go to mixers and then VCOs quickly, just to make sure that we cover all the topics that would be necessary to make an RFIC. And then I'll go back and start covering some more advanced topics for the last few weeks of class, just so we can kind of see what the contemporary, what some of the contemporary things are on RFICs. But I want to make sure those of you that have VCOs for your project have seen a VCO before you have to design one on your own, before your project's due. Okay. All right, so we'll stop there. Any questions from the audience online or in Torgerson? Yeah.
Other than mixing VCOs, what other like major topics are we covering? Are we covering PLLs?
I'll touch a little bit on the PLL, yeah, but by a little bit meaning I'll show you maybe a first order, maybe a second order PLL. I can do a whole semester on PLLs, so yeah. But yeah, we'll touch on what it is. All right, awesome. All right, so I will see you on Monday, if not before. I am definitely in my office most days now. All right, see ya.